Okay, let's begin. Aquaculture's water footprint, part two. So, one of the first references I'm going to use in this presentation right now is this series of books that's published every 2 years by the Food and Agriculture Organization of the United Nations. It's called The State of World Fisheries and Aquaculture, and people call it SOFIA for short. And so in this presentation, I'm going to be using 2014, 2012, 2016, 2018, maybe 2020, 2024. And the QR code is there to find all of them uh, if you want it directly. Otherwise, you just go there and you can find the entire knowledge base of the FAO and find these documents and much, much more. So what's interesting about this is it's showing the world per capita meat and fish food supply. And this was in the 2014, but the data is actually only up until about 2009, as you can see here. And as we notice from 1969 until 2009, this space of about 50 years, that aquaculture has grown from very little to quite a substantial amount, maybe 15–20% of the total almost. And poultry has also grown phenomenally. And so when we look at this, we see that okay, capture fisheries is there, and it's not changed much. It's going down. It's right below aqua there. And then you have things like bovine meat, poultry meat, pig meat, and so on. Now, pig meat has grown also, but most of this is due to the expansion of pig farming in China. But it's not particularly in going on anywhere else because most of the countries where world population growth is increasing the fastest, like Indonesia, Nigeria, many of these, even significant parts of India, are Muslim populations, and they do not eat pig meat. So what I wanted to really to show here is that if we talk about what kind of meat is going to be most important in the future, the trend here is clear. It's going to be primarily aquatic foods, seafood, and also chicken. So if we talk about the blue dimensions of aquaculture, okay, so blue dimensions typically is in reference to sustainability, but blue also refers to water. And there's the QR code if you want to find this. So this is very similar to what I showed you at the beginning, where we had blue water, which is surface water, groundwater, aquifer water. We have green water, which is taken up by terrestrial plants, and this is coming from runoff from precipitation, rain, snow, and glacial melt. So this actually, previously in part one, we talked about this was uh, actually included in green water. And then we have water, once the rain falls, the ground is saturated, we end up with a lot of soil water, and then of course at some point or another the soil is saturated, and then the water comes out. We also then have evaporation going on, and it comes back as precipitation. What's interesting for us in aquaculture is we're taking this blue water and we're using it for aquaculture. Now here they have wild fish, shellfish, and aquatic plants, and they talk about algae and also rice. Now the reason rice is here, for people who don't know, is that when rice farming starts at the beginning of the crop, the fields are submerged with water, and the young rice needs to be in water. But as the rice grows to, let's say, 20, 30, 50 centimeters or higher, then the fields are allowed to dry. But in the early stages, they use water. So moving on to another document, this one is for me a very interesting document. It's a little bit old now, but nevertheless, it's published by the World Fish, who are now located in Malaysia. And it's talking, as you can see, about the environmental costs of aquaculture. And so this was an early document looking at the environmental footprint of aquaculture. And so when we look at this, we're thinking here once again about use of water and where the water footprint is. We see here we have FW is freshwater and C is coastal water. And so in all of these graphs, you've got FW is dark blue and C is green. So if we look here at Asia first, we can see that India is almost all freshwater, very little green. And that's partly because most of the aquaculture in India so far has been fish, mainly carps, and more recently tilapia and pangasius. Where if we go down to some countries like the Philippines, down here, um, the Philippines are mostly green because they're growing brackish water milkfish as their main production. Uh, we see Korea here is mostly marine, and Thailand is mostly green, so mostly marine, but a little bit of blue. Now, in this case, green for Thailand is really focusing mostly on shrimp farming. Now we can go and look at other continents. We can look here in Europe. We can look here in um, Africa, and we can see, where the emphasis is, whether they're growing salt water species or whether they're growing freshwater species. So this is another document worth downloading. Farming the Waters for People and Food. This is proceedings of a global conference on aquaculture 2010. It was held here in Bangkok. I was able to attend it. It's one of these giant meetings with many, many concurrent sessions. And so I stayed around the ones that were relating to fisheries and aquaculture. And from this one, I wanted to show you this particular table where they're looking at total and caput per caput, so this is per capita, freshwater availability in the different continents. And I've highlighted in red here Asia. So Asia has a lot of water, more than anywhere else, but the population is so high because we're including China, we're including India, Pakistan, certainly Bangladesh, all of Southeast Asia, that the actual per capita use is very, very limited per person. Now, okay, this is total availability. It's expressed in cubic kilometers per year. But don't forget from part one that we saw this number that per capita average worldwide was 1,240 cubic meters per year. Where this one is in cubic kilometers. So in Australia and uh, Oceania, there's not a not a lot of water, but there's very few people in most of those places. So consequently, they have a lot of water on a per capita basis. Now, this paper, The Ecological Footprint Concept for Sustainable Seafood Production, our review. These people, Carl Folk and Max Trell, they write a lot of papers relating to water footprint and sustainability of aquaculture, and they're both names that you can look for in Google Scholar or elsewhere and find a lot of their writings. I really only refer to a very small amount of their work. So in this paper, what they've done here then is they have gone to uh, observe the data from this shrimp farming area in the Caribbean Sea. So you see, we don't have any, we've got some water here. Maybe there's like a canal running up into here, coming out into here, like a small river. Otherwise, they're dealing mostly with brackish water here. They may be mixing fresh water with seawater. And so what we then go back and look at is that they talk about for 1 square meter of shrimp farm, that they need to have all of these things, all of these water resources helping to sustain this 1 square meter here. So we have post-larval mangrove nursery, and we have mangrove lagoon, and we have marine ecosystems, and this is what we use for producing the fish meal. And we have agricultural ecosystems producing the uh, shrimp nursery, but that might also include some components of the feed. So you can see that when we talk about the shrimp farm, actually there's a lot of resources, water resources that are needed to support that shrimp farm. Okay, here we are. This is a paper about tilapia, so managing aquaculture for sustainability in Zimbabwe. Once again, you see here we have Carl Folk and we have Max Trell and we have Niels Kotsky, who was also on the previous paper. So here now we're looking at tilapia cage culture and tilapia pond culture. So one is intensive and one is semi-intensive. And so the top part here is intensive and the bottom is semi-intensive. So the feed is the same. Um, but up here you can see the details about the feed. 50% local fish meal, 20% local wheat or maize, and 10% soybean. And they talk about these are all local ingredients. Now, whether they're produced there or just locally available in the market, I'm not sure. And then they talk about the stocking density. So 380 grams of fish per square meter, whereas in the semi-intensive, it's only 1.3 grams of fish per square meter. So it's quite a big difference. And here's your cage, tilapia, 1 meter squared cage. And you see all of this water resources. This is for feed production. And then you have for feed production here, you've got phosphorus accumulation, and you've got these other things. Whereas when you talk about a semi-intensive in a pond, the water need is much, much less because of the much lower stock density. So you have phosphorus assimilation the same, you have oxygen, and then you have the uh, enlarged pond surface, 1 meter squared. Okay, so what they've done is they've just taken that and they've expanded it to here and just showing you the resources that are needed for that. So once again, we can see that there's considerable difference between freshwater intense and freshwater semi-intensive in ponds. Now, here's another paper. This one is from Mexico, and they're looking at the water, energy, and land footprint of tilapia aquaculture. And they're comparing the footprints of fish and meat. And I've only got one graphic to show you here. And so they're comparing three systems: extensive, semi-intensive, and intensive, and the water used to produce 1 metric ton of tilapia fillet. So not whole fish, but fillet. And the yield of tilapia, if it's done by, let's say, hand filleting, is typically around because the head is large. It's typically only around 43 to maybe 45% if they're good at their job. And so then we're looking at the same blue water, green water, and gray water. And we have a difference now between extensive, semi-intensive, and intensive. And you can see that the intensive has a much more significant water footprint. But the gray water of these two systems is more or less about the same. Uh, Now, this is an interesting report. I was a little bit surprised to see it. It was printed out by the World Wildlife Federation, and it's called A Business Case for Improved Environmental Performance in Southeast Asian Shrimp Aquaculture. And I have two graphics from here, I believe. So here we see water resource use in cubic meters per ton of shrimp produced. So this is going to be whole body shrimp. And they're comparing white leg shrimp and black tiger shrimp, two species, in Thailand and also in Vietnam. So looking at the top, we see that they're talking about dark green or blue is brackish water, and the light blue is freshwater. So we have white leg shrimp here and black tiger here. And so black tiger is typically grown in almost full strength seawater in most locations. But the production these days is very small, maybe less than 5% of Thailand's total yearly production is black tiger. Whereas in Vietnam, there's still a lot of black tiger are grown, and not as much as Vanamai though. But the thing is that the Thais are doing this very intensively here. This is maybe 200 pieces per square meter. This one might be 50, 60 maybe max. Over here, the stocking densities are quite low. In fact, for black tiger, Vietnam produces a lot of organic black tiger where the animals are basically only about one or maybe two animals per square meter in these large tidal ponds. And you can see here that the average freshwater use per ton of shrimp produced. So you see in black tiger, they're basically not using any fresh water. Whereas the Vanamai, the salinity is diluted down. And you can see in Vietnam, it's basically both are grown in diluted seawater. So this is the second interesting thing from this World Wildlife paper, and that is we're looking at shrimp production intensity in tons per shrimp per hectare. So this means from low intensity to high intensity in this direction. And then we see water burden, cubic meters times 1,000 per ton of shrimp. So what we see is at very low stocking density, you have very few shrimp and a huge amount of water. So that puts these numbers very, very high. And as we go to more and more intense, we have more shrimp in less water. Now, notice we're talking here about Thailand and Vietnam. And so Vietnam is the dark blue. And notice that the stocking densities in Vietnam are relatively low. Whereas in Thailand, there's a lot of animals that are grown at a very high stocking density. The comment from the World Wildlife Fund was if we really want to have the least impact on aquaculture, we should be doing on the land, on the water, on other resources, we should be growing at high intensity, high density, because all of our resource use is lowest per ton of shrimp produced. And that's an interesting paper, an interesting report. I'd recommend you go and download it because they talk about energy, they talk about land, they talk about feed use, they talk about FCRs, and they have a lot of calculations that they use, a lot of tables that I'm not showing you here to back up their conclusions. Okay, so here's one going back to This one is in Chile, talking about salmon aquaculture and coastal ecosystem. And so the thing that's interesting about this is they have this graphic, which really gives you an idea about the nutrient flows in the system. And so we have our feed and 100% of the nitrogen in the feed, 100% of the phosphorus in the feed. The harvest, or in other words, in the meat of the fish, the body of the fish, we only can capture 25% of the nitrogen and 23% of the phosphorus. We then have, okay, well, this part I'm not going to pay much attention to. This is about escapes and so on. But what we can see is that about 15% of the nitrogen and about 60% of the phosphorus is inorganic, and it settles out into the bottom. And then we also have dissolved nitrogen and dissolved phosphorus in the water, 60% of the nitrogen and about 12% of the phosphorus. So where would this come? Well, it could come from eat and feed and feces. It can come from respiration from the fish. It can come from uneaten feed. But the point is that this then can lead to, when it gets uncontrolled, to seaweed growth, algal growth, or eutrophication. But this just gives you an idea of when we put our feed in, how diverse, how scattered the distribution of the nutrients can be that we typically will classify as um, pollutants if they are in too large quantities. And then in the case of a sea cage like this, they would be monitoring, as you can see here, the water. And in some places, like Australia, if I understand it correctly, that they will have monitoring, and you will pay a fine if your phosphorus effluent is too high. Okay, so here's a paper that's looking a little bit into the future, responsible aquaculture in 2050. And I just wanted to show you one graphic here. And this, I think, is, you can find many, many, many graphics like this if you search in a search engine and look for integrated multitrophic aquaculture. So when they talk about integrated, they mean multiple species. So we've got fish here, and we've got mussels here, and we've got algae. This is brown seaweed or something, red seaweed growing over here. And when we talk about multitrophic, that means at all trophic levels, meaning from algae to filter feeders to vertebrates like fish. And we see that there are two things. POM is a particulate organic matter. Small is going, first of all, it passes through the shellfish. They can absorb a lot of it. And then whatever is done, if you have also algae, seaweed growing downstream of the typical currents where the typical current flows are, this can all grab a lot of these nutrients. So this is a ecological way to reduce the water footprint, at least from this perspective. Now we also have um, particulate matter that settles down through the bottom of the cage. And what they're showing down here is that then it is possible to develop aquaculture of invertebrates. So we see some crayfish-like, lobster-like animals down here. There's some sea urchins, and it looks like there's also some sea cucumbers here. And so this is a large particulate organic matter, falls down here, and this is food for these guys, or at least part of their food. So when we have this multi-trophic aquaculture and it's integrated like this, the technologies are well known. It's been done for decades and decades. Um, and this is certainly a trend. That's why they're talking about it in this paper up to 2050. This is a trend that we're going to see increasing because we can sell those shellfish. We can sell that algae. We can sell those crustaceans. And so they do a job for us, and then they benefit us by providing us with more productivity that we can sell. Now, this is a paper that I like very much. I actually intend to talk about this paper individually, um, focusing only on it. But here we talk about increasing pressure on freshwater resources due to terrestrial feed ingredients for aquaculture production. And the main author is Paulo here. So the first thing that they talk about is if you want to understand the impact of aquaculture on the use of terrestrial ingredients, obviously as a component of the feed, you have to look at where all of the aquaculture production is. And so carps are approximately 30% of all of the world's production. And then you have shrimps is around 17%, tilapia 13, catfish, that probably includes pangasius, 0.8, 10, and salmon, and so on. And so carps are by far the biggest percentage of production. Okay, so this is their graphic abstract. And the highlight, okay, so the commercial feed related water footprint of aquaculture has been determined. Terrestrial alternatives for fish meal and fish oil increase the water footprint. And this is really the key point I want to emphasize here. Economic water productivity may be reduced due to alternative feed formulations, and future growth of the aquaculture sector increases pressure on freshwater resources. So what do we see here? Well, we see commercial aquaculture feed. We see a reduction of fish meal and fish oil, but we see a corresponding increase in terrestrial ingredients, including terrestrial plant oils. And this is their little graphic here showing that capture fisheries has leveled off. Aquaculture is increasing more or less exponentially. And of course, the data only is ending here at 2000. And what they're concluding is that the status quo, meaning currently now with high fish meal feeds, we have a lower water footprint. And when we move to low fish meal, high terrestrial ingredient, we end up with an increased water footprint. And that's due to the fact that the water footprint then gets distributed around the world to other locations. And I've got a slide here coming up in a moment. Well, there are two things that we have to be very careful about. One is water pollution, because we're sharing this water and we're using it, public water, with other people. And then to solve this problem, we end up generating more gray water. And then also concerns relating to global warming, climate change, and so on, is that what about if we face issues of water scarcity? So here they're looking at water footprint on a species basis. So we saw that previous graph, that was feed production. So now we're going to look at the production water footprint, but on a species basis and also on a group basis. So here we see water footprint by species. So we have a lot of carps in this part of the table. We've got snakehead here. We've got uh, a number of marine fish in here. And then we have our crustaceans down here at the bottom. And you can see that uh, green water, I think, when we're talking about these marine fish, this is green water here is referring to seawater, as we talked about in part one, where these ones, the green water, would be freshwater. Okay, I hope that's understood. And, here we have these definitions of the water. So now if we look in total world production, And remember, we said that carps together were more than 30% of total world production of fish. You can see here that these three species uh, constitute a very considerable amount, where these other carp species are much, much less. And then we have tilapia, which is second after carps in terms of total world production. And so some of these are very low, almost invisible, because the production worldwide is very small. And then we have white leg shrimp, very high, because as you saw, after carps, it was the second largest uh, uh, feed production. And when we talk about feed production, we're talking about substituting terrestrial ingredients instead of using fish meal. And this is the last one I want to show you from here. So what they've done is they've gone to an FAO database. It's called AFRIS. This is related to um, fisheries and agriculture, and they have a lot of great information in there if you go and look for information about species. Lots of data, lots of formulas, generic formulas, premix requirements, and so on. So what they've done is they've gone into that database and they've picked their formula, AFRIS 1, 2, 3, 4, 5. And the difference in these formulas is that this is a high fish meal formula and this is a low fish meal formula. And so we have this trend, whether we're talking about um, this one here or we're talking about this one here, it's very obvious that as we decrease fish meal content and we replace plant ingredients, the water footprint of the feed actually increases. The water footprint of the aquaculture activity increases. Now here's a paper written by Wesley Malcorps. He's also a fairly prominent author in relation to sustainability in aquaculture. And this is quite an interesting paper because he's talking about a conundrum. And the conundrum is we think we're going to reduce fish meal, we're going to improve our sustainability. But when we substitute plant ingredients in shrimp feeds, we actually increase our environmental footprint in every respect. And so once again, we have our green water, blue water, and gray water. And in each of these, this is modeling, okay? He's got some data, but he's also basing on modeling. And as we reduce fish meal from 2016, 12, 8, 4, 0 in these four models, every single one of these things shows that as we reduce fish meal from 20%, this one is 30%, and we reduce down to 0, our ecological footprint, our water footprint increases. And just to bring that point home, this is a paper by Gillian Fry, Environmental Health Impacts of Feeding Crops to Farm Fish. Now, this paper is actually about the effect on human health in the producing countries. So we have America here, and we have Brazil here, and we have Argentina. And this is focusing on shipping feed ingredients to China. And they're dealing primarily with agricultural ingredients like soy and corn and maybe not so much wheat, because wheat is mostly going to come from Australia or from Europe. You see there's some flows here, but it's very minor compared to the big ones. And so when we look at the effect of the crop harvested area, all of these three countries have similar areas under cropping. USA uses a lot of irrigation, where Argentina and Brazil use very little. And then we see, due to fertilizer use, we see excess nitrogen on the landscape. Now that nitrogen goes into the water table. It drains off the land. Well, then we have an issue about the gray water coming from the agricultural production. And then we have excess phosphorus. So the thing is, we reduce here in Asia, we reduce the fish meal in the feed and we replace it with soy. And we then increase our environmental footprint over there. Now, when they're talking about health impacts, they're actually talking about the impact of the degraded water quality, and they're also talking about the effects of cancers and other diseases caused by the use of insecticides, pesticides, herbicides, and so on, which I'm not going to get in here, but I may choose to highlight this paper in a specific talk. So to summarize, and we're kind of thinking a little bit back to part one as well as part two, the water footprint of an aquaculture operation extends far beyond the actual location. I hope that I've been able to convince you of that. And I have already stated that we actually really borrow water. We don't really consume water. You remember we saw water being used in salmon, but it was related to the on land phase, not to the in cage rearing in the sea. So we borrow this water and we consume it, and we have to take care of this water. We have a lot of shareholders, a lot of stakeholders that share that water with us. And if we want to improve our productivity by increasing our intensity, then our effluents become more concentrated. And if we wanted to, for example, expand our farming area, we've got 5 ponds, we want to make 15. If we irritate all of the neighbors that we share that water with, when it comes to some kind of a community decision, they will say, no, we don't want you to make our environment worse. So that's why we need to be good neighbors. We need to return the water to the environment at least as clean as we found it. We need to minimize dissolved nitrogen and phosphorus in the effluent, and we need to do wastewater BOD and COD. Now I have another video here in the sustainability area as well, and it's talking about the environmental impact of aquafeed. And I go into the detail about these two characteristics a lot more there. And then as we talk about reducing fish meal, reducing marine ingredients, and increasing terrestrial ingredients, we make our Asian aquaculture footprint primarily through the feed an intercontinental footprint. So thank you very much. This is a marine cages in Sardinia, which is an island in the Mediterranean, part of Italy. And these were cages being used to grow gilt-head sea bream. I had a chance to visit this farm a few years ago. And so there you have it. That's the end of the two videos on water footprint. Now, as more data comes or something else comes up more interesting, I may choose to uh, bring in a part three. But at the moment, I've got this data, and if I did another one, I would want it to be maybe more unique. So we'll have to see what I can find. So thank you very much for watching, and I appreciate your participation in my channel very much. I can be found also in Apple Podcasts, and I can be found also on X and also on LinkedIn.